So today, what I'm going to talk about is a bit changed of the tone of a very theoretical sort of issues about haptics. What I'm going to do today is virtual reality technology, which is possibly a tool, a useful tool for doing visualizations and possibly an enabler for doing digital training and to do, remote planning, visualizations, and human interactivities with remote systems, machines. I started working with, as a robot engineer many years ago, graduated from the Oxford Robotics Research Group, and then working in UKAEA for some time. I actually brought a picture of my time, 30-something years ago working in UKAEA in tele-operations. You can have a look at this picture with some force feedback, local and remote machines connected together. In the past 15 years, I actually started from a hobby of working with virtual reality and then started to build systems which try to realize the concepts of VR, virtual reality, with my students in the university. And then in the past 5-7 years, the tools becomes the product, and I was very happy that some of my students actually take on this and spin off their own company and then actually market some of the pictures that I'm going to show you a little bit later on today about that. So what I want to do to share with you my experience in this area, as I say, this is going to be very light touched. No equations, unfortunately, for those who are really hot on, getting proof and derivations of, control systems, haptics, and whatever. I'm sorry, I don't have any of those. Here we are. I use the topic super reality for remote collaborations. What is super reality? It's just a term that somehow, when I left the university, coincidentally, we were awarded very big projects with a number of universities in Hong Kong as well as University of Glasgow to build a super reality interface to connect laboratories across different territory to enable university students to perform haptic and other experiments through using robotics, haptic joysticks, and others, because it's not easy, for example, for students in Hong Kong to have such laboratories, and somehow laboratories, maybe in UK, in Imperial College, and some of those places, have those laboratories. Why don't we connect those up using communications together with good visualization aid, VR, so that students can feel what they're doing in the laboratories. And that's called the word super reality. It's not just a term. So today's agenda, I'm going to talk a little bit about my understanding of what is virtual reality in particular. And I hope to give you some use cases which is related to virtual reality, probably not that much on robotics alone, because virtual reality is very wide in scopes. And then I will go into a little bit more serious issues about the problems, the limitations of using virtual reality. And in the past 10 years, I've been working with educators, working with medics, working with psychologists, working with engineers, of course, to try to dig out, for example, when we actually use head-mount display, okay, like Oculus, HTC Vive, and some of those. Why do people actually feel dizzy? Cyber sickness is actually one of the key issues of deploying good virtual reality systems. Although you may find that, okay, the system we built, rover and other, very powerful. You can have a 3D perspective of what the system are. If we're really going to use virtual reality, or people say augmented reality or other more seriously, and you are going to operate the machines for 10 hours a day, putting on head-mount display. Can you bear with that? Virtual reality system is designed for people to use. And if we cannot actually make the system which is effectively, comfortably to be used by people, I don't think we have successfully technically to develop those systems. And for example, cyber sickness is actually one of the key issues of why we are so feeling uncomfortable in using those systems so far. Even if you play games, you may not like it after a while. Why don't people just use your mobile device or computer to play games rather than putting those head-mount display? I'm sure you don't need to have a kid to tell you, but you probably appreciate it's so uncomfortable. So we are still a long way there. In terms of some of the background, virtual reality, there's some concepts and terminologies. A lot of people say, no, this is AR, this is VR. Oh, no, today we should talk about XR and all this. I think to me, if you put things into perspective, I think you can actually put things into some sort of continuum. Before going too far, if we Google, go into Oxford dictionaries and others, there are a lot of terms about, for example, a computer-generated digital environment, virtual reality. But looking back 100 years ago or 50 years ago, computer graphics, 3D graphics, isn't it already virtual reality? Another more conceptual thinking is about how about if we build things which is not real digitally through a computer? Isn't it that's already the virtual world? However, if you, like me, as an engineer, we want to be more formally talk about that, looking at the picture on your left-hand side, this is an airport, the real airport. I would call this is a real environment. We work with Cathay Pacific, for example. Some years ago, we tried to build a virtual airports with virtual machines for training their ground operators. Everything is generated in computer. This is virtual environments. If we try to mix both real and virtual, for example, one of the use cases we do is we built a cargo airplane door control systems because the ground operator need to operate the cargo door to load air cargo onto the plane. Now, as you can appreciate, using a real airplane just for training is expensive. Even parking a parking space for a 747 aircraft for doing cargo loading and unloading without any errors, accident or something like that is going to be tricky. It's expensive. So what Cathay Pacific commissioned us at that time is to say, can we use VR to do that? Rather than using all this head-mount display, because the trainer and the operator and all this cannot see each other easily. What we do is that we build a cave, which with projection, synchronizations, we build screens for the street walls, the floor and ceiling to project a synchronous image of an aircraft, and then put a real cargo door control panel and then integrate it in the right perspective so that the operator is touching with good feel of the control button, but operating the virtual cargo, virtual door, virtual rollers, and all this to do that. This I will call, augmented reality. Some people say you augment what to do, but the more generic term is what I call mixed reality. You mix real and virtual. So if you look at this real reality, virtuality continuum, you can nicely put all these terms across this and then saying to people, no, I'm referring to this is AR, this is VR or something like that. To me, virtual reality is actually encompassed a very broad spectrum of, for example, my student is actually looking in a cave. If you carefully look at it, this is probably the third generation cave that we developed. There is edges here simply because you can see the connective between the wall and the floor, and it's not that continuous, but the graphics, according to his perspective, is pretty continuous. So he is engaging or immersing in its own world. So there are three main components of virtual reality as far as I define it. First of all, is immersion. Immersion is technical, is technology. How well you develop the system, which can trick your sense, in particular your visual sense, to see, okay, if I project things on the floor, on the three walls, on the ceiling, and then matches it so well, and synchronize my perspective and movement so well, as in the CAVE system. CAVE is actually an acronym for CAVE Automatic Virtual Environment, CAVE. The first paper that was presented for CAVE is from 1991 SIGGRAPH. Okay, it's special interest group in computer graphics, which is a very big conference for those who work in computer graphics. SIGGRAPH is as good as top journal if you can publish in SIGGRAPH. In 1991 SIGGRAPH, EVL from University of Illinois in Chicago, they actually, a bunch of researchers from the electronic visualization laboratories conned the first implementations of the CAVE automatic virtual environment, which is exactly what is this, is a projection-based system which project images that synchronize along the wall, ceiling, and all this. The people, when you go in, is so good that you can feel yourself is in some sort of virtual environment. The other thing is more psychological, is the presence. Well, if you always tell yourself, even how real, how realistic the environment is projected, if you always tell yourself, you are not in that environment, you will never feel so true. Presence, on the other hand, is psychological. If you imagine yourself that you are in that environment with the good technology that replicate the sensation that give you visual, sound, smell, movement, for example, then you feel much better that you are immersed or be present in there. To me, the most important factor is imaginations. Imagination is inside you. Is inside you. The more imagination you could, I think the limits of virtual reality is actually only limited by that. Sorry, let me go back here. Yes, I think the best virtual reality system is that. I got a little dog, not here in Hong Kong. When my dog is dreaming, I think my dog is actually in the best, most perfect virtual world. He can feel, can see, can whatever, being chased by me, for example, not being naughty or something like that. And in future, I think the best virtual reality system is something like that we may take a medicine and then we go into a zombie state and then we feel so real. If you imagine you are in a dream, you are chased by something, you probably feel the pain or something like that. That's the virtual reality system that we perhaps will go for. For example, if you want to go into virtual world, you have some electrodes or something like that, and then you do that. That may be crazy, but perhaps. Actually, virtual reality is not new. When I look back in history, I put some link here, I can share some of those. The slide can be shared, no worry. In 1980, I beg your pardon, this is wrong. 1849, it should be 1849, it's not 1949. 1849, people already trying to build gadgets which have the same concepts of a head-mount display, which give you a stereoscopic visions so that you can see deafness in them. That's the Bruce stereoscope, which is working there in the 1980s. A more engineered, devices, which is designed by Sunderland in 1968. This is 68, but the first paper that was presented at that time, 65, is what they call the ultimate display. The display actually is a little bit more complicated. The interesting bit is the motors and the gear train that's on top of the head. This is actually a mechanical gyro, which actually, not gyro, but it's a position devices that measure the head orientation so that as you move along your head, the graphics or the display changes. think about it. A very good virtual reality system is that as you go along looking at a particular device, the perspective change, the actual graphics that should actually give you into your eye should change as well. So you need some measurement of where you are. The system downstairs in the work hall got a lot of OptiTrack systems. The OptiTrack system is a motion capture device which can capture where the users are. So the graphics will change accordingly in real time so that it replicates our vision perspective of that. So those are some of the technology that we need to do that. Well, this is the very first cave I built in 1999 with my students. 1999, think about it. We are not too far off. 1991, the first paper, Cave in SIGGRAPH. 1999, we replicated it in the University of Hong Kong. This is a projection-based systems with screens and with a computer engine which can produce synchronized images at the moment across the 3 walls and the floor. There's no tracking system, there's no 3D graphics, but just an environment that people sit there, be able to appreciate the sensation of a very immersed environment. During that time, I think, those are all the professors. They are having fun. They all sit on the ground, and then I try to, explain a bit to them what they're after. And they say to me, Henry, you write more papers. You stop playing computer games right now, That's the thing. Okay. But here you are. We are spinning off 3, startup, and then marketing all this technology, 20 years later or something like that. So it's not just computer games anyway. Okay, that's what we have behind the scenes. We use barcode projectors and that. Okay, this is generation 3 cave. All the views are virtual. There's no real stairs. There are nothing real in there. You see the lady walking very slowly up the virtual stairs. And then now she tried to go downstairs. This is not an actor. She's not trying deliberately to try to act. But you see, she walks so slowly simply because if you have been walking up a plane in that sort of stairs, you can feel the steepness of the stairs. And she was so worried. Wow, as a bystander, you feel this is good fun, seeing her acting like this. But to her, to this lady, I think she feels so real of the height and also going down the stair without being able to hold the rail. Okay, going down. And you can see the scenes actually changes. To her, the stairs, the airplane, everything is stationary. Just that as she moves along, her perspective changes. The graphics synchronize to where her perspective are.
Jet engine in the background.
Huh?
You have the jet engine in the background as well, the noise.
Yes, we reproduce all this. So this is a virtual environment, not just visual, sound, but sound only. I don't put a motion platform on. There are some systems that I put motion platform on, for training or something like that. But anyway, that's real enough. Experiment told us that vision itself actually reproduce probably over 70% of our sensations in the world if we don't have touch, which is not necessary at that time. Okay. This is the newest generations of cave. This is an LED-based 3D cave. I am in this environment, very real. We can replicate all this. Although I am, I think it's possibly the speed of the graphic card. But you can see I seems to be interacting with very realistic environment. Because LED technology, this is 3D LED, so in theory, we can put on 3D glasses and 3C, deafness. This is a very simple version of it that we made in the university. So summarizing some of the technology innovations that, oh sorry, I think we need to, right, let me turn it down a little bit. So what you see is that this is the training systems for Cathay Pacific. We are using not just VR, but later on I will also show you a little bit about what makes virtual reality useful. For a training system, it's not just the visual and coordination that we want to train. We also want to know how well the behavior of the individual who is working in the virtual world. So we need to actually capture the behavior and be able to profile how well the particular trainee is doing using some means. Obviously, you can stand a number of trainers and then try to do the normal training procedures by taking marks and all this. But as a researcher, I think it's nice to actually have some AI to do it. So we incorporate artificial intelligence with VR to make a fully autonomous system for capturing the behavioral profile of user in virtual environments. So this is one of the training systems that we've been developed. And I share a little bit of those insight a little bit later on. The other thing is about these concepts of digital twins. Now, this is one of the thing is that, okay, to create everything virtually, and then you go in there, that's fine. But how to coordinate and how to synchronize the real and virtual environment at the same time. We need some way of getting real-time informations of our real world to the virtual world and vice versa. This experiment was done some 4 years ago using those depth cameras, which sold from Xbox, actually Sony Xbox. Those what you call Kinect, right? This is using first generation Kinect, but more than one of those. So the image that is displayed here is a 3D image of point clouds. So they are color point cloud, which is captured from a couple of Kinect sensor somewhere across the laboratories. And the image is displayed here. I'm actually wearing 3D glasses and seeing what over the other side is doing in 3D. And then I communicate with my student here as well. And then there's a couple of Kinect actually, capturing my images and then send it across to his side. So this is something of an early implementations, I would say, implementations of the digital twin systems.
Henry, it's a quick question. How far were the real system?
For this, it's very close. I'm saying it's the other way. So we are not using particular high bandwidth communications. We are just using, okay, if you look at this actually stands out. So it's not far. But the project that I'm going to just describe a little bit, the super reality laboratories is actually cross-country and cross-continent. So it couldn't be done. It can be done. So those are the Kinect systems, right? Yeah, this is from a news channel we are doing a press conference to show at that time, we could do that. And then Hong Kong people say, wow, we be able to say, no, this is old days technologies. No big deal, I think, okay. Right, okay, here you are, Salvador, just answering what you're doing. Giving all these bases, why don't we extend it and try it in a more lighter touch? Okay, we are not doing sort of surgery or something like that. We're just connecting laboratories together. And then we coin the term, in order to get the grant, we need to dream up nice term. I'm saying we'll probably know it very well if we're just using the old name, virtual reality for hands-on laboratories or something like that. The funding body would not entertain us, So, a couple of us sit together and then one professor would say that, let's use super reality, make it super. Not XR, not AR, no, there's super reality, a new term. So we say, good, let's use super reality, and then we got funded. Okay, that's good. This is actually facilitated by COVID, actually. What happened is that 2 years ago, the eco funding body as EPSRC in Hong Kong, They put forward these big grants, bids for COVID related projects, and then we feel that, because of COVID, our students cannot travel to laboratories across the world to try to appreciate the labs. So we say, let's put together a super reality hands-on laboratories that connects our laboratories. Somehow we got a partner in Glasgow University, Imperial College, so we just, try to do that. Some people in China as well, and some in Japan. Let's link them all up using virtual reality is one of those. Haptics is another. And then what we want to extend it to why we super reality is because we want to give experience for students the feel of subatomic particles. For example, when we do nano manufacturing, normally you cannot feel the molecule, right? But through electron microscopy, we can actually capture the profile of those, electric cloud or field or something like that. And then we try to expand that and then put in the haptics as well so that the student can feel the shape of, molecule or something like that. And that's another gimmicks of performing experiment. So this super reality interface not only limits to what you appreciate using, data gloves, head-mount display, but it also extended to, other feeling in terms of motion, the touch. You got 3D video, the sound, you got the smell, and all this. Just a way to bundle, all the sensation across. The thing is, sorry, I go too far. Let's go back a slide. Here you are. You will see. For example, this is the nano manufacturing of semiconductor materials. So through a electron microscope, we can see the profile. And isn't it nice that if we can send the things across to other places for students to feel? Some of our researchers already working on cooperative robotics. This is one of the laboratories in the US that couple of Puma robots, pretty old robots, is trying to handle a big piece of things. Can we try using people from another sort of place in another laboratories, and two students try to tele-operate the two robots and to handle some large piece of materials, what the sensation and what this is going to be. And then this is a bit newer technology. This is the ABB robots. It's just a pair of ABB robots, and then it's trying to pick up, some sort of cylinder. On the other hand, this is in Hong Kong, so the student actually sees through some head-mount display with data gloves, and then they try to replicate, try to control what the robot is doing. So this is very conceptual, experimental. I don't see that is, real applications. However, this is a little bit more interesting. This happens in my labs. This is 2005. This is a WAM manipulators that we bought from the US. And then there's a phantom joysticks. This version obviously is different from that version. This is a 3 degree of freedom, phantom joystick. The other one, we strip out all the electronics because Sensible technology didn't give us the innings, so we built our own drive systems and then all the electronics and then connect it directly to the WAM manipulators. The WAM manipulators is a US manipulator developed by Ken Salisbury from MIT with his student, Bill Townsend, and it's a cable-driven manipulator. WAM stands for whole arm manipulators. Why is it whole arm manipulators? Because of the low friction of the cable-driven system, which Will has explained quite a bit in the earlier series of lectures. So the motor current is usable for reflecting the touch along the whole mechanical arm of the manipulator. I tried it, it's not bad actually. the WAM. This is a very early version. This is probably the first generation WAM manipulator that we have got. Now they use this plug drive system and all this. You can just carry it, you know, the WAM manipulator is as small as that. But at that time, what we tried to do is to connect the phantom joysticks. It's a 6 degrees of freedom phantom joystick. You can see a force shock sensor, the ATI force shock sensor we still use today, and try to do a combinatorial of implementation of various force control algorithms to try to achieve high fidelity, you know, force feedback operations or teleoperated operations. Seems to work, not bad. So we are not, you know, basing ourselves on totally, you know, unused ground. So this project started in the middle of 2020, so it's still in the very early phases. So you see those are some of the very experimental, you know, setup. So there's no connections at all across at the moment that up to our standard. What we try to do is that the internet that's connect different continents is fast with 5G and all this coming. It's not bad, but not too reliable. Sometimes you may get delay, you may get error. So one of the work packages that the Glasgow University is doing is that they're working on an optimal way of sharing load or try to distribute load on the internet connectivities. They're not working on robotics. They are actually experts in the communications, 5G communications. So what they try to do is to look at the task and try to predict the loading and then try to share out what data you got to share to send through, okay, at that instance, but keeping the control in sort of pseudo real time, I must say, you know, so keeping the time state good so that you don't have inherent unpredictable uncertainty in the delay when you try to operate remotely, okay? So part of their work packages is to look at, you know, how to best predict the traffic of the communication systems and how to actually optimally distribute the data package across that. So it's an interesting project. Now, all these are research. Let's look at some real use cases, how we use virtual reality, in particular in Hong Kong, I must say, at that time. First of all, something good fun. I don't know how many of you have been to Dun Wang caves, which are the cave that's inside, you know, some of the places in Yunnan in China. Most of the caves are closed now because of the carbon dioxide erosions or contaminations in there that erode the picture. But what we do is we work with the Buddhist, you know, authority to reproduce the Dun Wang cave in the cave digitally. And people can virtually now visit Dun Wang cave in facility with cave now. So we don't need to fly to Dun Wang to do that. And then we actually perform classes and all this to share this with a number of universities through some cloud platforms. And this is the virtual reality cave systems that you see here. Another one, using virtual reality with the airport authority to do emergency drill. So what they do here is to connect different virtual devices together to run all this emergency drill. I think according to the International Aviation Authority, every airport, international airport, need to conduct an emergency drill every year to make sure that they know what to do if there are situations. But this is horrendously expensive, disruptive. Probably now it's not that disruptive because airport in Hong Kong is not used a lot. Because of COVID, they closed the border. But in the old days, to conduct real emergency exercise, I've been a couple of times in midnight when they closed the airport with over 20 government department, fire services, try to do the drill. I think it's very expensive. Now, using virtual reality, I think using Cave, Google, and other virtual devices to cooperate among people, for example, how to deal with, you need to evacuate people from airport using buses, and also you can capture the behavior digitally of individual trainee. I think that's useful. So this is being sort of cooperations that we have been working on using virtual reality technology with the Hong Kong International Airport. So for example, this replicate a fire in one of the people movers between terminals. So they need to shut it down, and then the big boss saying that, look, all this works very well. Anyway, that's the conceptions of that. As I say, Cathay Pacific actually use this as well for doing the training. So yes.
One question from the previous. So is it being accepted? So they are not anymore doing physical drills?
No, they still do it. But what they do is that they will do an assessment of some of those virtually first. And then they still need to perform the real thing, because that's the rules and regulations of international aviation. But it saves a lot of time, and they can repeat small exercise with much cost-effective means for doing that. So this is what I'm talking about. The panel is real. That panel is real, but all the cargoes, all the plane is virtual. So you can see this is what I call mixed reality training system. So this video is actually made by Cathay Pacific. So they're actually using it for doing the regular training in the airport. And we built the big cave for them in the airport. Happy to move up. Okay, so in the case, okay, this is another simulator for air bridge training system. So operator actually remotely operate the virtual air bridge, which allow passengers to go off the airplane, because air bridge again is very expensive resources in airport. There's not that many free parking space where people can exercise the air bridge. So a virtual one using virtual reality. This air bridge simulator actually has something more than just the visual and sound. There's a motion platform. There's a 6 degrees of freedom steward platform that sits on top of that. So as the operator operates the virtual simulator, the floor actually moves together with the visual. So you can feel real scenarios using this simulator, right? Okay, use cases, theory. Now, issues. I think there's many more issues that when we start to use VR seriously. Here you are. While people feel that, oh yes, very nice, interesting, embodiment, meaning that, oh, I feel so real in there. However, how good are they? It's very good, for example, for very casual, use. There's very good for, 3D visualizations and all this. They're nice. However, in terms of transparency, usability, stability, and how natural they feel, if we really look deep down into, some of the issues, then we will see that while the benefits are there, for example, the use cases I show you, okay, the lab, the training system, all this, we can actually make it more cost effective, but how sustainable, how usable is that? Here you are. Some of the key issues include, for example, after people use it for some length, maybe half an hour even, they feel nausea, they feel dizzy, they have a headache, and then they feel that the user interface, all these gloves, all this head mount is unnatural. Why do I need to cram my head into that to see the images? And there's a big disengagement between real and virtual as well. For example, head mount display. I'm immersed in the virtual world, but I cannot actually talk to people around me easily. So, given those issues, how do we actually look into it? I think I'm going to highlight two aspects. One is how we capture user behavior. That is what I call profiling, behavioral profiling. In a virtual environment, how we gauged how we behave in the virtual environment. The other is to look deeper into the cause of cyber sickness. What actually causes us? What actually causes us? The dizziness. First of all, in order to do that, first of all, the first issue is how do we capture or characterize human performance in virtual environment? Okay, how well do we do? How well do we do? Now, in order to do that, I think we need to not just, try to say how quickly, how well, how accurate you do those steps, but to monitor our physiological, this sort of output. For example, how much our eyeball actually moves before we actually start to initiate the feeling of cyber sickness or something like that. How about our pulse? How about breathing? How about all these things? So can we start to characterize it, model it, build a model of our feeling, and then try to say, okay, you have been working in virtual environment too long. You are going to initiate those feelings, stop using it, take a rest or something like that. So a project is to try to use this multiple modality recurrent neural networks to, I think it's better to show you a picture rather than equations. As I say, I'm going to skip the equations. How to measure, for example, your body movement by measuring your balance through using some balance board. Because, for example, when you start to lose balance, maybe that's a trigger for starting to get, dizzy. Looking at eye movement, perhaps you start to not spending your concentration on that. Maybe EEG, those signals that capture from that, and then try to train the neural networks to try to learn the pattern so that you know for yourself when you should start to use, stop, or your performance start to degrade when using your virtual reality devices. The other things that we work with Cathay Pacific in particular is to build this AI empowered system using artificial immune system. What we do is that, for example, let me go back to this picture. For example, this guy is trying to perform various steps, various issues in a virtual environment to perform his task of handling the air cargo. How well does it do it? Okay, that's good thing. It's like assessment. But more importantly, is that fewer and fewer people would like to do this type of jobs. We need to retain their skill sets so that either you train more people to go into the job, but you need to find qualified trainers to do that. How about you capture their skills digitally? Okay, somehow, when you do it, this is a skill operator. Before he retired, let's capture all his skills digitally. And then we can use that digital profile of his skill to train more people or retain his skills so that we can have a reference for doing that. The way to do it, how we try to do it, is to use AI to try to, spot the salient behavior. Artificial immune system is one of those AI methods which I'm sure you know what immune system is. Immune system are the defense of our body. It's a decentralized system. For example, if an antigen comes into it or bacteria come to our body, somehow the immune system can identify those antigens, bacteria, or whatever, and then try to coordinate actions and then take some actions. Now, this, if I look into it, it's very much like if you look at knowledge identifications or try to do anonymity detections, it's like hidden Markov model, which you have an observable behavior, but deep down is actually what that trigger the observable events or things. So artificial immune system actually works something like this to try to pick out, for example, if the skilled worker is doing that, what is he actually intend to do, or what is the important step that trigger his action. So that's why in the VR system, we try to use the motion capture systems to capture the superficial movement and then try to identify the salient or more important movement so that we can capture a digital copy of what the actual skills is. It's not just the movement. You don't just repeat the skills, but you want to understand what the more deeper meaning of the skills using AIS or artificial immune system. I've been in AIS for some time actually, so there's a number of publications, on that. Lastly, I want to talk a little bit about cyber sickness, which is the more recent works that some of my students or co-workers still working in the laboratories in Hong Kong, is to look at what trigger or why cyber sickness. Let me tell you one of the very interesting findings we have got. Now, I'm sure most of you or some of you have used head-mount display to see VR images. When you put on your head-mount display, you look at those stereoscopic images, real, with 3D, with depth informations. After a while, you feel dizzy. One of the reasons is that when you put on head-mount display, you cannot see your nose. You cannot see your nose. But naturally, we see our nose all the time. And we are actually seeing our nose, but intuitively, we know our nose is here. We see it, but we don't recognize it. In a VR environment with a head-mount display, the nose is not drawn in the virtual image, so we lose the nose. Missing a nose in the virtual world actually triggers quite badly cyber sickness. So what we do is that we draw a virtual nose in a virtual environment, and that actually improves the usability. And this is a major finding. We've published paper in Display, last year, and seems to be one of the highly cited paper so far in virtual environment. So there are a number of, concepts. Sensory conflict is one of those. For example, our ears, our eyes didn't match. For example, in the roller coaster, a virtual roller coaster, we didn't move because our ears didn't display anything, but our eyes seeing all these images, that's trigger cyber sickness. You can appreciate that quite quickly, okay, in games, but there are others. Posture instability, for example, our ability to stand still, but if our sensory system say that, no, you shouldn't stand still, that will trigger cyber sickness as well. And then, let me go back. Here, come on. Presentation. Here you are. Yes, getting back. Eye movement hypothesis. The ability to fixate our eyes on objects which are having a certain field of view is important. If we give too much things for people to track, you start to develop cyber sickness as well. So that's why a lot of head-mount display actually restricted your field of view to reduce cyber sickness, to reduce eye movement as well, which subconsciously you may not be aware. So in addition to the nose issues, there are a number of very scientific studies that can help us to develop more usable virtual reality system, which we may not aware initially. So here you are. This is called, the nose issue is called self-referencing. Self-referencing. We need to have some self-reference. In addition to redraw our nose, we can actually put some fixed objects that we naturally do that. One of the experiments that we do is like that. This is a motion platform. We strap our, by the way, this is one of our volunteers. It's actually my PhD student. She wants to strap herself, and then we try to move it, and then put a goggle. And then what we want to replicate is that when you travel on the boat, how come when you try to look at the horizon, as compared to you go into the cabin without being able to look at the horizon, you can develop seasickness quicker? Simply because this is self-referencing issues, that you can see some self-reference. And then that's help our brain to cope with the certain motion that you don't feel, ears and eyes seeing images. So experimentally, we see that out of a big bunch of volunteer, this is a significant, statistically significant sort of issues. So all this will show, again, this is another field of view study. You can restrict the field of view, and then you can try to put people through, and indeed that will give all these sensations. And then again, another device that we developed, again, to look at eyeball movement and try to trigger all this. Oh, by the way, initially I know nothing about this, not until we work with the psychology department and the medical department. They actually give us a lot of insight, and they've been doing that, and then we cooperate in there to try to actually dig out a lot of the thing that intuitively in their mind, which should be done, but is actually proven using technology. So, final couple of slides. How useful is VR? I see there's still a long way. Technology, for example, if you look at HoloLens 2, which is one of the top AR device that we use. I tried it a year ago, still too heavy. Field of view is improved, but still we need to strap things on to see the AR images. How do we actually, realize digital twins, for example? There's many issues. For example, how we synchronize real and virtual, how we replicate the physics, how we synchronize the continuity between real and virtual. That's the issues. To make it useful, for example, how to make all these visualizations and collaborations, and try to make VR useful tools so that people accept it is probably another big issue. Of course, there are challenges. For example, how we actually make comfortable system, usable system with little cyber signals, that's psychological issues. The other is technology readiness, how much acceptance that more wider public actually want to use virtual reality for doing that. The coexistence between real and virtual is still an issue. For example, augmented reality is useful in certain extent, for example, for navigating across uncharted terrain. Then the indications or the predictions that give us the prompt to give us the additional information would be very useful. But it's not too real if we really look at real augmented reality. Hardware, maybe material science, still limitations of doing that. Looking forward, I think virtual reality cannot stand alone. I think we need to work together with a bunch of technology before it's going to be making it really useful. VR, in the end of the day, is a tool. It's a good concept. It's a good concept. Remember the three components: immersion, presence, and the limits of imaginations. This is a really nice concept that put people into this computer-generated world. But not until we can bundle, it's a system integration problem. Not until we bundle it with, for example, artificial intelligence, very good communication, what Salvador just mentioned. How good is how far, how do we channel the data across seamlessly, quickly, in a high bandwidth manner? Human-computer interactions, head-mount display is too bulky. It's not too useful. All these devices, if we want to make it very natural, for example, if you touch this touch this table, the haptic devices that give us the resolution, the sensation without wearing a lot of bulky and heavy glove, put on a lot of vest, I think it's still a long way. Not until we can actually try to bring all this in and try to design around this technology, I think there's still quite a bit of way using virtual reality as a whole. So thank you very much for the time. I really enjoyed the moment. And of course, as I say, I'm going to share the slides with everyone. And thank you very much indeed. Thank you. Right. Is there any questions?
I think one of the big issues here is Q conflict, isn't it? So you talk about cyber sickness, that's Q conflict. the woman walking down the stairs, she was able to deal with cue conflict. Because going down the stairs, your feet usually go down, but in her case they weren't. But she was still getting the visual cues.
Yes.
But that's still a conflict.
Yes.
So one case, cyber sickness, you feel ill. The other case, it just adds to your ability to build up this world.
Yes.
So perhaps there's something in just looking at, rather than cyber sickness, looking at all the times you can get away with cue conflicts, and all the times you can't get away with cue conflicts.
True, very true. One thing I personally experience is that the more I've been trained or getting used to that, I think I can suppress some of those more obvious conflicts so that I'd be feeling less, uncomfortable when using that. The ability to identify, what are the key conflicts that is more important to people, I think that's something that is going to be very interesting, I suppose.
Yeah. So, I mean, there's an interesting anecdote I've heard about a training system, and it's sort of similar to this idea of a table, that if you've got a VR table, you can't lean on it. And the same sort of idea is they had a training system for servicing aircraft, and they pulled out the rack of electronics. And in VR, that's fine. You pull out a rack of electronics. On the rail system, this rack has weight, and suddenly they realized that they didn't have enough strength to hold the rack in place. Again, it's when can you get away with cue conflict, and when do you have to do something about it in your virtual reality?
Right. This is very much quiet. I don't know, with astronauts training, they do a lot on Earth using training. They try to replicate this weightlessness and operating on this. Yeah, I think it's an issue how much we can implant those into our brain, saying that now you're expecting this and to do that, yeah.
And I think that comes into the idea of transfer. So the training system in whatever environment, does it transfer into another environment or into the rail situation?
Or what bit can be transferred and how?
How do you ensure that you get the right bits transferred?
Indeed, this is a very important issue, like what we are doing here, isn't it? What are the bits that we can really replicate effectively using this type of technology? Yeah. Cool. Thanks, Will. Right. I'm sure, we are all enraged anytime, I suppose, anytime if there's any, discussions, issues, I'm sure I'm most interested to keep my technologies of interest.
Well, can I just ask a quick one? With regards to this long distance teleoperation that you were mentioning before, something I'm really interested in actually, and we have done some work in collaboration with our institutions, and we found that one of the biggest issues is, of course, the network. You were mentioning something very interesting, that some of the parameters you're transmitting from one location to the other are like you're working on the optimization of the packages that you are sending and all that, which is actually very nice. I wonder if during your work you consider, this is something that came to our mind at the time, like using some sort of semi-autonomous system working together with a teleoperator, which for in cases that you actually lose track of because of latency, because of anything, lag, there's something that at least the system is not lost. Because something that we experience is, I'm talking about only control signals, not even vision. The robot, for example, start doing some weird motion because of the lack of the control system, control inputs and so on. So I don't know if you also did some work on that, or on adding some sort of semi-autonomy to the system together with that.
Of course, to share the intelligence from the local and remote and try to give a little bit autonomy to the remote systems so that they'd be able to identify any abnormal signals that's going along or breakages so that they don't suddenly do, or should they stop, should they continuous, or something like that. This is probably something that in this super reality laboratory project is going to explore once the first phase of each laboratory is geared up for the first layer, and then doing the predictive things and then giving some autonomy. How much autonomy that's going to do that? I'm sure in the equivalence in the telesurgery systems, that's even more important. That, for example, if there's a network glitch or something like that, when the surgeon's doing something, should the robot actually continue to, should they halt or something like that? I think the system is going to be very conservative and probably not. I don't know. I frankly speaking, I don't have too much further information with regard to that at this stage about the strategy of giving what degree of intelligence or autonomy to the remote side.
We could work on that later.
But that's very much depends on the task, maybe sometimes task specific as well. Yeah, thank you so much. Yeah.